First is an electric diesel plant supplies energy primarily during a 24-hour period. The plant consumes 20-40 gallons of fuel at 28 degrees Celsius and produces to 3,930 kilowatt-hour. Industrial fuel use is 28 degrees Celsius, so the API end was purchased at 30 per liter at 15.6 degrees Celsius. What is the cost of the fuel to be produced in kilowatt-hour? So this is the formula. So it will be the 141.5 divided by 131.5 plus 28. So the answer is 0.88887. So the density at 15.6 degree Celsius will be 0.8887 times 1 kilogram to 1 over 1 liter. So the answer is 0.887 kilogram per liter. So the SG at 38 degree will be 0.887 times 1 minus 0.007 times 1 minus 15.6 is equal to 0.87. So let's start with the V. So V will be 237.835 gallons times 3.78 liter per gallon is equal to 900.21 liter. So let's stop the cost. So the cost is 30 times 900.21 over 3930 will be the 6.87 kilowatt hour will be the final answer. So an hydroelectric power plant is 30 square per kilometer reservoir area, and the 100 meter head is used to generate power. The energy is utilized by the consumed loads connected to the power plant during 5-hour period is 13.5 by 10.6 kilowatt hour or kilometer. So the overall generation of efficiency is 75%. So let's have the energy output. So will be watt times Q times H is times time. So that's 13.5 times by 10.6 is equal to 9.81 times Q times 100 times 0.075 times 5. So the final answer is 3669.725 cubic meter per second. So let's have the volume. So 3669.725 times 5 times 306,000 is equal to 66,555,000 per cubic meter. So 66,050 times equal to 30 by 10.6 is equal to 2.202 meter. So an hydroelectric power plant having is 30 square kilometer reservoir area and 1,000 used to generate power to utilized by the consumer where load is connected to the power plant during a 5-hour period in 13.5 by 10 kilowatt hour. The overall generation is 75%. Find the fall of the height of the water reservoir after the 5 hours period. So let's have the area reservoir. So the area reservoir is 30 kilometer squared. So it will be 30 by 10 to the power of 6 cubic meter. It could be meter squared. So fall in height, so it will be 66.2 times 10.6 meter cubed. So 30 by 10 over 6 meter squared. So it will be, the answer is 2.21 meter. An amount of air with 130 temperature of 35 degrees Celsius, wet bulb temperature at 28 degrees Celsius, as passed through an air condition at TV temp of 24 degrees Celsius and RH of 50%. The cooling coil temp is approximately 18 degrees Celsius. Determine the bypass factor of an air conditioned system. Enthalpy difference will be the 55 kilojoule per kilogram minus 90 kilojoule per kilogram, and it will be 35 degree. It will be negative 35 kilojoule per kilogram. So the enthalpy difference due to cooling is equal to 90 minus 45 is equal to 45 kilojoule per kilogram. So by factor, so let's divide it. So negative 35 kilojoule per kilogram divided by 45, it will be 0.78 is the answer. So a 20 mile per liter wind at standard temperature and the pressure passes through a horizontal wind turbine. The wind perpendicular to the blades, and the turbine has a blade diameter of 30 feet. Air temperature and pressure are 70 feet and 1 atm. What is the most nearly approximate power that the turbine can generate? So let's have the wind speed. So 20 mile per hour is equal to 8.99 times 1 mile per hour. So it will be 0.447. So the blade diameter will be 30 feet. So let's convert it to meters. So 9.14 meter. So the area will be the pi times 9.14 meters squared is equal to 65.97 meters squared. So what, and the Betz limit will be 59.3%, and the air density is 1.225 kilogram per kilogram cubic meter. So the max power will be, let's have the max power, so it will be 0.593 times 0.5 times 1225 times 65.27 times 8.94 is equal to 15,400 watts. So let's convert it into horsepower. So 15,400 watt time divided by 745.7 watt is equal to 20.6 watt.